Hello everyone. As I'd mentioned in the previous video, we'll be discussing the graphical analysis. We'll be dealing with graphs. Okay, so the graphical representation uh, comprises of obviously the two axes, that is the x and the y axis, where the x axis is independent and the y axis is dependent. Now independent because its value changes independently. It does not depend on anything or any other factor. Okay, so its value changes as it is, but the value of the y-axis, okay, it may depend, sometimes it may not depend as well. So it may depend on the value of the x. Okay, so in kinematics, the x-axis, the independent axis, is the time axis, as time is independent, as we all know, it carries on itself. And the y-axis, that is the dependent axis, may have a position or displacement, as we call it, because for a body object which is moving, okay, its position varies or changes with time. And the y-axis can also be, the dependent axis can also comprise of speed or velocity, whose value changes for an accelerated motion. Okay, so let's take an example for understanding. We are taking this as the first case, where we are checking with the variation of position with respect to time. So we have the plotting of the time over there. Time is taken in seconds, and the position is taken in meters. Okay, now if we say that the position does not change, suppose okay, we take the initial position at, suppose 3 meters, as I have pointed the arrow over there. So the body lies at that position of 3 meters when the time t is equal to 0. Now if it remains at rest, its position won't change with time. So in the first second it remains at that point, that is 3 meters. Okay, in 2 seconds as well, it remains at that time 3 meters. 3 seconds and 4 seconds, 5 seconds, likewise its position does not change. So if I now plot the graph, I get a straight line over there, and that straight line is a straight line curve parallel to the time axis. We call it as a curve because even if it is straight line, what we plot in a graph is known as a curve. So we get a straight line curve. Again, suppose we take a second case where it starts to move, and this time it moves with a constant speed, and we take the starting position as a 0, yes, at the origin. Okay, so the starting position is 0 at the time t is equal to 0, right? And we are taking the case of constant speed, means its value is changing equally. So it's traveling equal distance in equal intervals of time, right? That is what we know about mean by constant speed. So let us suppose I take a value that its speed is 1 meter per second. That means it is traveling every 1 meter in every 1 second. Okay, so in the first second it goes 1 meter. So the coordinates, as you can see, is 1 comma 1, that is 1 second and 1 meter. 1 second for the time axis and 1 meter for the displacement axis or position axis. Then at time 2 seconds it goes further 1 meter up, that is 2 meters, then 3 meters at 3 seconds, 4 meters at 4 seconds, and 5 meters at 5 seconds. So likewise we get these kind of points, and if I join those points, I plot a graph which is now a slope. So it is a straight line which has a slope or a slant, as we call it. Now what is the value of that slope? How do we calculate? Now the value of the slope is usually calculated by del change in y by change in x, that is del x del y by del x, and here del y by del x is nothing but del s by del t. So, and del s by del t, as we all know, is the velocity. So the slope of the position time graph gives the speed or velocity of that object. And how do we calculate the slope, value of that slope? Now the slope will be calculated here as del s, that is the change in position, and the del t, as that is the change in time. As you can see, del s and del t have the values 1, so which is 1 meter per second. 1 by 1, it is equal to 1 meter per second, which is the value that we had taken in the beginning. Okay, so that is the constant speed of 1 meter per second. Now if the body is accelerating, Now suppose I take a number that it is accelerating at 1 meter per second square, and its initial speed is 0 when it starts, that is at a position s is equal to 0, and time t is equal to 0. Okay, so position initially is at the origin, as you can see. At time t is equal to 1, we can just straight away put the equation of motion s is equal to ut plus half a t square, and since u is equal to 0, it is 0, so we have the value to be equal to 0.5 meters. So at 1 second it is somewhere between that 0 and 1 in the y-axis, that is the displacement axis, and it is 0.5 exactly in the middle. And at 2 seconds, again if you see, it's a square of 2, that is equal to half of 4, that gives me 2 meters. So at 2 seconds it is at 2 meters. Then again at 3 seconds if I consider, then the value changes to square of 3, and we have half of 9 over there, so it changes to 4.5. so the position is 4.5. And likewise at 4 seconds its position is 8 meters by calculation, as we can see. Now if I join those points that I have obtained, now this is the curve that we are getting over here, and it's not a straight line. Obviously, as you can see, it's not a straight line, it's bent, and so the speed isn't constant over here, obviously, because the object is accelerating. How can the speed be constant? So graphically we can understand that how things are changing. So but how do we calculate the speed at any instant of time? Any instant of time means we are calculating the instantaneous speed. So how do we calculate this instantaneous speed over here? So let us suppose I want to calculate the instantaneous speed at t is equal to 3 seconds. Now how do I do that? Now at 3 seconds, that particular thing that I've ticked over there, that 3 seconds time, I consider that point on that curve, and at that point I draw a tangent. As if you can see, I've drawn a tangent over there, very thin line, and I take a slope, right? I take a slope of that tangent, and the slope of the tangent is obviously del s by del t, which gives me the speed at that particular instant of time. It's easier if we, and precise if we are drawing it on a graph paper or a plotting paper, that we can consider where the points have been given. So but mathematically we can calculate it just like that. In plotting papers it's easier. Here it's a rough diagram, so we do not have the exact points over there in between small squares and big squares, but mathematically obviously we can calculate by the equation of motion, that is v is equal to u plus at. So at time t is equal to 3, acceleration being 1 meter per second square, so we have 1 times of 3, that is 3 meters per second, with the initial speed at 0. Now again we consider the velocity versus time graph, velocity or speed versus time graph, and at constant speed, just like for a constant position when the body was at rest, here it is the constant speed that we are considering. The value doesn't change with time, and hence we get a parallel line parallel to the time axis. It's a straight line parallel to the time axis. But in the position time graph, when we had considered the constant speed, if you remember, just now we had studied, we had obtained a slope over there, right? Starting from the origin that I had taken in the example. So but in the speed time graph, here it's a straight line, it is parallel to the time axis. Now there's something else that we can consider over here, is that as there's no acceleration, we can simply have without the equations of motion, that is v is equal to s by t, that is position by time or distance traveled by time taken. So s is equal to v times of t. So at any instant of time we can calculate the distance or the displacement. But how do we calculate that? So we calculate that by using this particular value, that is s is equal to v times of t. So at that time, suppose t is equal to t, that I have marked over there. So the speed, as you can see, is over right up above it. So v times of t is equal to s, which is nothing but, in this graph as you can see, it's nothing but the area of that rectangle which is under that slope. The slope is a straight line parallel to the time axis, and the area under the slope is a rectangle. And what's the value of that rectangular rectangular figure? That is v into t, right? So v times of t, that gives me the displacement. So it is always the area under the speed versus time or velocity versus the time graph that gives me the displacement distance or the displacement, right? These are few points that we need to consider or remember. Then we move over to the next case where I consider uniformly accelerated motion. Now in the previous case the velocity was or the speed was constant, but here the speed is changing. And how is it changing? It's changing equally in equal intervals of time, because we have considered uniform accelerated motion means the acceleration is constant. So we get a slope having some finite value, that is obviously we take the initial speed. If we take the initial speed to be 0 at time t is equal to 0, so we start from the origin over there and we get a slanting line, straight line. And what is the value of the slope over there? It's del v by del t, because y by x as we know it. And what is del v by del t? It is nothing but the acceleration, and the acceleration here is a constant one. Okay, its value isn't changing, so the acceleration is constant. In kinematics, as I've told you before, that right now we are focused on constant accelerated motion, and we are not going further into variation in the acceleration, right? So that's how we consider things graphically, the graphical interpretation of things. Now consider a very small time interval. If you see, that has come up over there, and in that small time interval I have shaded a very small portion which is almost the shape of a rectangle, very thin, so I can consider it to be a rectangle. And hence, because the area under a slope being a rectangle gives the displacement, so that rectangle also will give me displacement. And consider many such small rectangular areas under that triangular slope. If you see that, adding one after the other such small rectangles, we can get the net displacement. So here in this case we can calculate the net displacement by considering such small rectangles under that slope, and now as you can see the figure is a triangular one. Okay, so we can derive the equations of motion graphically as well. Okay, there are methods to do that. So do write in the comment section if you want to know the derivation of the equations of motion by graphical analysis. Else we'll proceed and with the problems, and then further into the topic. Okay, till next time, thank you for your patience. Goodbye.